What is matter? What is antimatter? At first glance, they seem like mirror images. Every particle that makes up you, me, and the stars, electrons, protons, neutrons, has a shadowy twin with the same mass but opposite electric charge or quantum numbers. An electron's twin is the positron. A proton's twin would be an antiproton. When a particle meets its twin, they can vanish in a burst of energy, annihilation, returning their mass to pure light. It's a dramatic reminder that, at the deepest level, matter and energy are interchangeable. How are they made? In the simplest laboratory picture, create enough energy in a small volume and matter appears. This is pair production. High-energy photons, intense bursts of light, can convert into an electron and a positron, obeying energy and momentum conservation. The reverse process, annihilation, turns a particle-antiparticle pair back into photons. The equations of quantum field theory make this dance of creation and destruction routine. Energy, particle plus antiparticle. Yet that tidy symmetry contains a cosmic puzzle. The fundamental laws with important caveats treat matter and antimatter almost equally. If the early universe started with pure energy, hot, dense, symmetric, we might expect equal amounts of matter and antimatter to form. Then as the universe cooled, they would annihilate each other, leaving behind nothing but light. Clearly that didn't happen. Here we are, made of matter, living in a matter-dominated universe. Where did all the antimatter go? Physicists call that the baryon asymmetry problem. Baryons are the family that includes protons and neutrons, the stuff of everyday matter. To explain the imbalance, Soviet physicist Andrei Sakharov proposed 3 conditions any successful theory must satisfy. Processes that violate baryon number, creating more baryons than antibaryons, violations of charge parity symmetry, CP, a subtle preference that makes matter behave a bit differently than antimatter, and interactions out of thermal equilibrium. In plain English, the early universe needed mechanisms that gently favored matter over antimatter and did so under the right hot and changing circumstances. We've found hints of how nature could do this. Experiments in particle physics have observed CP violation, a tiny skew in certain particle decays that treats matter and antimatter unequally. The standard model of particle physics contains CP violation but not nearly enough to account for the overwhelming predominance of matter. So the search is on. New particles, new interactions, exotic decays, or events during cosmic inflation might amplify the imbalance. Ideas like leptogenesis propose that an asymmetry first arose among neutrinos, very light ghostly particles, and later converted into the baryon asymmetry we see. None of these ideas are confirmed. The mystery is alive. That gap between equations and existence is where physics nudges into philosophy. Why did anything survive annihilation? Why is there a universe capable of hosting galaxies, planets, and conscious beings? The fact that a minute, precise imbalance, perhaps one extra particle per billion particle-antiparticle pairs, can tip the scales from nothingness to a cosmos teeming with structure is humbling. It suggests that existence may hinge on delicate initial conditions and subtle laws that favor one outcome over another. There's a poetic current here. From symmetric laws and violent annihilations, a tiny asymmetry births everything. The early universe was a crucible where chance, symmetry breaking, and the arithmetic of quantum fields produced the raw materials for stars and life. In that sense, the question why is there something rather than nothing becomes a question about tiny physical biases and the cosmic conditions that magnified them. We don't yet have the final chapter. Ongoing experiments, at particle colliders in neutrino observatories and in precise cosmological measurements, continue to probe the mechanisms that could have created the imbalance. Each new clue will narrow the space of possibilities, bringing us closer to understanding how a universe of matter rose from an almost perfectly symmetric beginning. So the next time you look up at the night sky, remember, the galaxies glitter because the universe chose, however slightly, to favor matter. That infinitesimal tilt, a microscopic preference written into the laws of physics, is the hinge on which all of existence swings. The mystery isn't just that particles exist, it's that the cosmos preferred one mirror over the other, and from that tiny preference everything followed.